Okay, so we're solving the last situation where we have just one eigenvalue, and actually it's going to be more specific than that. Let's consider the difference between x prime equals 1001 times x versus x prime equals 1101 times x. And let's see what the difference is. In this case, right, before I write down my characteristic equation, let's go ahead and it's a good idea to write down your trace and determinant first. We'll be doing that later as y. Trace, determinant's the same. So lambda, oops, that's not 0. That's 1. Okay, lambda squared minus 2 lambda plus 1 equals 0 means lambda is 1 and 1. And so this is going to give us the same solution. So we're going to have lambda equals 1 and 1. And so if I try to plug this into my system of equations, I get, if I plug in lambda equals 1, I get 0 equals 0. So what are the v1 and v2? Well, v1 and v2 are free to be anything. So this is really the first case where we've seen two free variables when we solve this. And so what's typical is to take v1 to be, for example, 1, 0, and v2 to be 0, 1. Although you could take v1 and v2 to be any two vectors that are non-zero and not multiples of each other. Okay, and then our solution is actually case 1. That says that our solution to the system is going to be c1 e to the t times 1, 0 plus c2 e to the t times 0, 1. Okay, so this is not a special situation. If you get the same number of eigenvectors as we had eigenvalues, but that's not very common. What's probably more common than that is to get a double eigenvalue but only one eigenvector, and by that I mean let's go ahead and plug in let's compute our system of equations. 1 minus lambda v1 plus v2 equals 0 in this case. 0 v1 plus 1 minus lambda v2. And so this equation goes away, but you are left with v2 equals 0. And so that is a restriction on your v's, and so your eigenvector is only one eigenvector in this case. Right? I'm just scaling this out so the first coordinate is 1. And so now the question is what do I do? I only have one eigenvector, but I have two eigenvalues. Okay, so that is the situation we're in. A single eigenvector, two eigenvalues. So I'm going to go ahead and just state the solution to this. It's very much like we did in chapter 3, where you basically have to state the solution and then double check it by plugging it in. And so we're going to do something similar. We're going to say that the solution is x of t equals e to the lambda t times x0 plus tw, where x0 is the initial condition and w satisfies the relationship that a minus lambda I, we're going to, do you recognize that notation? We're going to write that out. Oh, maybe I should just go ahead and write it out. Sorry about that. A minus lambda x0, I'll go ahead and use x0 plus b y0 equals w1 cx0 plus d minus lambda y0 equals w2. Okay, so you see that this is almost the same as our eigenvector equation, except we're using our initial condition here, and we're also putting our w's on this side instead of 0. Okay, so in terms of our previous problem, right, we had our eigenvector was 1, 0. What would this look like then? Well, this would be 1 minus lambda times x0 plus 0, plus 1 times y0 equals w1, and then 0 times x0 plus 1 minus lambda y0 equals w2. And so you see here, right, that what's your w1? W1 is equal to y0, w2 equals 0. Good. And so this is your w now is y0, 0. And so the solution, the previous solution to x prime equals 1, 1, 0, 1 times x, with x of 0 being x0, y0, is given by x of t equals e to the t times, I'll go ahead and write it out, x0, y0 plus t times y0, 0. Good. And that is your solution. Good. And notice that this solution is in terms of the initial condition. All right. And so let's try this again here for another equation and see if we got it. So example, how about, this is kind of a weird one, but that's good. Good for practice. 4 minus 2, 8 minus 4 times x. And we see that our trace is 0, and the determinant is minus 16 plus 16, 0. Oh, that's okay. That means just that lambda is equal to 0 and 0. And so what do we do in that situation? That is a double 0. So we check our differential equation to make sure that we're not getting two eigenvectors, right? And so we would have 4 minus 0 v1 minus 2 v2 equals 0. And then the second equation would be 8 v1 plus minus 4 minus 0 v2 equals 0. And what do you see here? 4 v1 minus 2 v2 equals 0, and 8 v1 minus 4 v2 equals 0. So this is a condition, and so I only get one evec from this, right? That's all the information I really needed, because now what we do is we form our equation a minus lambda x0 plus by0 equals w1, and abc plus d minus lambda y0 equals w2. Okay, good. And so our lambda here is equal to 0, and so we get oops, darn it, get rid of that. Something happened to my, where's my OneNote? There it is. Sorry about that. Let's get back to our solution here. This is going to be 4 x0 plus minus 2y0 equals w1, and down here we will have 8 x0 minus 4y0 equals w2. Good. And so then our solution is going to be x of t equals e to the t, e to the 0t, which is just a constant, times our x0, y0, plus t times our w, which now is 4x0 minus 2y0, and 8x0 minus 4y0. Okay, so this is our solution. By the way, what does this solution look like? If you were to plot this, this is a straight line in the plane. So our solutions are very different in this situation. We don't have an exponential function, so our solutions are lines. Alright, so this was kind of a special case. Okay, so we're going to summarize all of these different cases in chapter 9 when we get there. And so we've just finished chapter 7. So now at this point we should be able to solve x prime equals ax for all three cases. We should be able to graph solutions in cases 1 and 2, but not necessarily 3. This case is kind of a hard case typically to write or to graph, and so we're not going to focus on graphing those solutions. But I think if you can graph solutions for saddles, sources, sinks, and spirals, then you're looking good. Okay, so that's chapter 7 at this point. I think we're going to pause here. I'm going to have some notes online where we just mix up all kinds of different systems to solve and plot for homework. Okay, so when we get back, we're actually going to be starting to solve nonlinear systems of differential equations. And so that's going to be starting chapter 9 of our textbook. See you then.